Good evening. So our first lecture is the introduction of matrices, definition and basic operations. I should say here that the number of the section here is identical to the one from the book where the homework is taken from. That's not gonna be important, obviously, for those of you who watch this and are not my students taking my class. So let's start with the definition. A matrix is simply a rectangular array. It's a tableau, basically, of numbers or symbols in general, mathematical symbols, arranged by rows and columns. It's as simple as that, and we're going to see some examples as a motivation in a minute, although you might imagine easily that the sky's the limit in terms of the number of examples you can come up with that may necessitate such an object, right? The arrangement of data by rows and columns. It's important to point out that as a rule of thumb or as a convention, we will always mention the rows first and then the columns, and that will have some implications on the standard notation related to matrices. So let's give a quick example. For instance, if this tableau, this array 213601 is a matrix with 2 rows and 3 columns. We can also say that it's a 2 by 3 matrix. Another way to denote matrices is by using capital letter. So I could basically take another example. Let's say matrix A given by 6, 1, 2, 1, let's say 0, 2. This is a 3 by 2 matrix. Again, we always by convention specify the number of rows first and then the number of columns. It is also practical to work with some standard general notation. This can be a little bit tedious or more, let's say, quite formal. I'm going to try to avoid as much as possible too much formality so that we can get very quickly to the actual examples and basic concepts. But it's still necessary to denote a matrix in a general term. So for example, in terms of variables or in terms of unspecified numbers of rows and columns. So for now, let's say with this second example, if these entries of the matrix are not specified or are given by variables, a convention of notation for those variables is to use the double index notation for that variable. So it is common to denote, so let's call it standard notation of entries of big A. It is common or common convention to use the same letter as the letter used for the matrix, but small letter with the double index notation, something like this. Little aij, in which I represents the row number and j represents the column number. So in this case, in my example, I will be from 1, 2, and 3 because we have 3 rows, and j will be from 1 and 2 because we have 2 columns. And of course, we could write the full matrix in terms of variables: a11, a12, a21, a22, 31, and 32. If you see this for the first time, it's important to pause the video. I don't take breaks because I know people can always pause the video to catch up. So there's no reason to make the video longer than it's necessary. But notice here that if you go by row, obviously the first index is always the same. If you go by column, the second index is always the same because the second index represents the column number. So in this notation, for example, A22 is going to be the element 1, and then A31 again, using my example, my second example, a 3, 1 will be 0, right? So the element of the entry on the row 3, column 1. So that is the general notation, and this is how I'm going to refer to a matrix from now on if I want to refer to it in general terms. So generally speaking, let's write it down here. Generally, M by N matrix, that is to say M rows and columns, is denoted by some capital letter A and by the generic element small aij, and then we specify the range of I and j. That is to say the number of rows and the number of columns. In this case, 1 to m and then 1 to n. So let's get straight to, well, we're going to get straight to matrix operations in a minute, but let's actually define another subtype of a matrix, another quite an important subtype of matrices, namely a row or a column matrix. So if M is equal to 1, A is called a row matrix, right? So if you have just one row, if instead N is equal to 1, A is called a column matrix. You'll see that in some contexts they can be used interchangeably. So here's an example. If I have, let's say, the matrix 1, 2, 3, that's going to be a column matrix, right? It's of a type 3 by 1, but obviously if it's a column matrix, you don't really need to specify it has only one column. I mean, that information is already built into the title, so to speak, or into the name, because it's a column matrix. So you only specify the entries in the order they are given, top to bottom if it's a column matrix, or if it's a row matrix, let's say minus 1, 3, 5, and 2, that is going to be a row matrix, which is basically 1 by 4, right? I mean one row, which is again not needed to be specified because we already mentioned it's a row matrix, and instead it has now 4 columns. So these matrices, the row or the column matrix, is also known in some contexts as a vector. We will define what a vector space is more formally later on, but many of you already have seen this concept before. For example, an arrow with magnitude, right? I mean, obviously, right? So an arrow that indicates a velocity, for example, or an acceleration, that's an example of a vector. And if you represent it in space or in a coordinate system like 3D or a two-dimensional system, you can represent it in terms of the coordinates of the point, which it becomes then a column or a row vector, depending on how you write it. So this is what I want to point out, that in some contexts, actually it doesn't matter, just in some contexts, whether you write it by column or by row. For example, if you talk about vectors, many operations or many problems can be done by, writing the vectors as columns or as rows, and it makes no difference. In other cases, it does make a lot of difference, whether they are arranged by rows or by columns, or whether these, vectors appear as rows or as columns. So with that out of the way, the next part of this lesson, I mean, of course, the remaining part of it, and the biggest chunk of it, I should say, is dealing with basic matrix operations such as addition, multiplication, dot product, and so on. So usually I don't know if I have time to go over what I'm going to say right now in class, but since we have the time here over the internet, I like to actually give a practical motivation behind some of these matrix operations, because I think it's important to understand that they serve a specific purpose, more than one purpose, but it's just not for the fun of it. For example, we could start by defining how matrix multiplication works, but I think it won't make sense to understand why it's defined that way if you don't see actually a practical example. And that actually will help me a little bit when we move on to the definition of those operations, because we can actually present it in a much more compact and faster way. So I think it pays off. So let's take a step back from the abstract part, and let's look at, let's say, a motivating example from economy, if you want, although maybe that's too big of a word. But let's say, for instance, you have to collect data to plan selling of products for a store, for a grocery store, for example. And then let's say one data point for that store is just, let's say, the quantity expected to be sold in a day for a given product. So let's write it down here as quantity sold in pounds. And we do this, I mean, we present this information for a variety of products, and so that we don't waste too much time, let's say I present it for 3 types of products: apples, let's say pears, and plums. So naturally you end up with a row vector, with a row matrix, right? Let's say you would expect to sell 10 pounds of apples, 5 pounds of pears, and then 2 pounds of plums. So obviously matrices can be used to represent data points, right? In this case, the quantity is sold in pounds for each product. And let's say another type of data point is the unit price. So I'm going to write it here on the right hand side here, the unit price for the same type of products, for the apples, for the pears, and for the plums. And let's say the unit price for the apples, forget about whether that's realistic or not, let's say it's $2. For pears is per pound, right? It's $3. And then for plums is $4. This is per pound. So if someone wants to compute the revenue, it shouldn't be too difficult to understand that this is a summation of products between the quantity for each product and the unit price. 10 pounds of apples times $2 per pound, plus 5 pounds of pears times the unit price, $3, and then plus 2 pounds times $4, the unit price for plums. So the total revenue in this case is going to be 20, 15 plus, let's see, yeah, 20 plus, sorry, I wanted to make 20 here to make it a little bit different than the price. So let's say 20 pounds of plums, because I don't want to be as small as the unit price. All right, so 10, 5, 20, the quantity, 2, 3, 4, the price. So we have 20 plus 15, that's 25. 35, sorry, 35 plus 80, that's $115. So you will see immediately this on the next page. This is just an example of a dot product, or a scalar product between 2 row vectors or 2 column vectors. This is one type of the operations we're gonna talk about. And as you notice in this very simple example, it can have a practical meaning. Not the only one here, but one practical meaning, like you see here, is just price, or excuse me, the total revenue. If you look at the data points for the quantities and the unit prices separated in these 2 row matrices. And finally, with this motivating example, notice we can actually extend this to a more complex set of data points. And keep in mind the way I arrange it, because it will make sense later. let's say, for example, I want to make projections. What if I have various days with different expectations of quantities to be sold? Maybe some days are expected to be or are poorer in terms of the quantity sold, and also I want to experiment with different unit prices. So in such a case, we can generalize this example in the following way. Let's say again, for the quantity, instead of a row matrix, I have a full matrix with multiple rows. Let's say on a given day, on day 1, let's say I'm expecting to sell the quantity I mentioned before, 10, 5, and 20. Again, for the apples, pears, and plums. But say in another day, I expect to sell less, and then I have 5 to 10 pounds of each. Once again, these are apples, pears, and plums in pounds, right? The quantity, right? This is the quantity in pounds. And then let's arrange also in multiple columns the unit prices. And the reason I arrange them by columns, you'll see it has to do with the way the matrix operation or multiplication is defined, right? So what if I have different set of unit prices in which, again, this time let's put the apples, the pears, and the plums by rows, and the unit prices, let's arrange them by columns. The first column with the set of unit prices I used before, but let's say I want to see another set of unit prices to analyze it cheaper. Let's say $1 for apples, $3 for plums, and then $2 per pound of plums, or $3 for pears, and then $2 for plums. So now we have actually two matrices, and if we could do this, if we do these dot products by combining rows and columns, we actually compute the revenue under various scenarios. Day 1 with the first set of prices, day 1 with the first set of prices, day 1 with the second set of prices, and then the same combination day 2 with the first set, and then day 2 with the second set of prices. So in that case, I have basically another matrix that encapsulates the revenue under these scenarios. So let's write them down one more time. So we have 10 times 2 plus 5 times 3 plus 20 times 4. That's the revenue we computed before. Or we could use the second set of prices, 10 times 1 plus 5 times 3 plus 20 times 2. And now I take the quantity sold in day 2 and then again combine it to see the revenue under the two set of prices that I have here on the right hand side. So 5 times 2, 2 times 3 plus 10 times 4, and then 5 times 1 plus 2 times 3 plus 10 times 2. Okay, so if I simplify this, obviously in the first corner here I'm going to end up with what I had before, 115, because I computed that before. For the second set of prices we have 10 plus 15, that's 25, plus 40, that's $65. The other one, 10 plus 6, 16 plus 40, that's 56. And then finally 26 plus 5, that's 31. Okay, so the take-home message on this page is that all of these operations we're going to learn will have a meaning in practice, in real life, even though in this class we're not going to spend time to do word problems because we don't have the time for that. Okay, that's, again, remember, 1 hour credit class. So stay tuned for the second page, for the next page, to continue with the formal definition of these basic operations. All right, so let's start with the sum of two matrices. It's important to understand that not any two matrices can be part of an operation. There has to be some condition satisfied on the rows and columns. That's one important consideration. for the addition or the sum of the two matrices, we require two matrices of the same type of rows and columns, so the same number of rows and columns. So as a definition, suppose we have an m by n matrix with the generic element a, I, j, and b same type m by n matrix denoted by bij, right? So the generic element. So once again, we're not going to specify this all the time, but by that I mean I is from 1 to m and j is from 1 to n. So with these notations, the sum of the two matrices a plus b is the matrix with the element aij plus bij. So you simply add the elements side by side, or entry by entry on the corresponding row and column. Let's go straight to the examples right away. So suppose we have a given by 1, 2, minus 1, 0, 5, 1. So that would be a 3 by 2 matrix, and b with the entries minus 1, 3, 0, 5, and then let's say another one, minus 1, 3, then a plus b is going to be 1 plus negative 1, 2 plus 3, minus 1 plus 0, 0 plus 5, 5 plus minus 1, and then 1 plus 3. Let me point out that in the beginning, once we do an operation for the first time, I basically write it like that explicitly, like, or in, let's say in a slightly more detailed way than necessary, really, just to see how the elements are formed in the operation. Because after that, for the next examples, we're not going to have to spend time to do this. We could simply compute in our mind 1 minus 1 is 0, right? That's not worth splitting into an extra step, so to speak. So that gives me 0, 5, minus 1, 5, and 4, 4. Now, another basic operation that will appear in many applications is the so-called multiplication by a scalar. By the way, these are operations that are kind of intuitive. If you ask a student, how would you define the addition of two matrices, even if you don't provide that student with a definition, it feels, let's say, intuitive or obvious, or however you want to call it, that you're going to add component by component to these matrices. Now, realize that not all operations are as intuitive as this one, but summation of two matrices, the multiplication by a scalar, these are two types of operations in which it kind of makes sense that's defined the way it is, right? So, as you might expect, in the case of a multiplication by a scalar, you actually multiply each entry by that scalar. So let's formally define it. Let's say we have a matrix A with any numbers of rows and columns, doesn't matter, and a scalar, which, by the way, in our context is another name for a real number. It has a more general meaning than that in abstract linear algebra, but for now let's just use it interchangeably with a real number. And by the way, the name scalar is because actually this operation is used to scale vectors or matrices. So it kind of makes sense to call it that way because it's more in tune with the way it appears in applications. So a scalar denoted by, let's say, little c, right? A real number. Then we define the product between a scalar and the matrix as the matrix formed by multiplying each entry of the matrix by c, by that scalar. All of these formal definitions are best to learn by looking immediately at an example, right? Because it's often much more suggestive than the formal definition. So let's say let's say C is -2 and then A is equal to -5, 1, 6, 2. You'll also notice that I often use the 2 by 2 matrices if I want to save some time, because sometimes the notion is pretty straightforward, that it's not worth spending time to write, let's say a 5 by 5 example. So we multiply the scalar -2 by this matrix. That means, as the definition implies, one multiplies each entry by that scalar. All right, so in this particular case, therefore, CA is going to be 10, -2, -12, and then -4. All right. One important remark is that scalar multiplication of matrices is often appears in reverse, and often that's actually more useful in some contexts. So let's say I start with a matrix 50, 100, 200, and 150, and that's why it's called a scalar multiplication, because it's each term, each entry is actually scaled by that common scalar. It's like taking apart the common factor. You notice that 50 is a factor of each entry. So in fact, you can pull it out in the form of a scalar multiplication factor. So if I pull 50 out of each entry, obviously, and if you want to do it correctly, you have to pull it out of all entries, then you're left with 50 scalar multiplication with the matrix 1, 2, 4, and 3, right? 50 times 3 is 150. So often this direction is more useful because it allows you, and that's quite important trick to keep in mind, because it allows you to actually simplify your computation. Often, if you have to do some other computation, it's easier to work with 1, 2, 4, 3 than the original larger numbers. So now we come to two important operations that are not as intuitive as these ones. Before I move on to that example, though, let me just state here that the order of operations is the let's say it's similar to the one for real numbers. And this can be proved formally, but we're going to just take it for granted, meaning that you do the multiplication before you do the addition. So as an example, with the matrices on the top here, let's see which example shall I pick here. Yeah, so let's say I want to compute 2a plus b. Now 2a is a scalar multiplication. So look at matrix A first. So that gives me 2, 4, -2, 0, 10, and 2. So you do that first. And then you do the matrix addition with B, which is -1, 3, 0, 5, -1, 3. And so when you add together, then you have 2 minus 1, which is 1, 4 plus 3, 7, -2 plus 0, 0 plus 5. And then finally 10 minus 1, which is 9, and then 2 plus 3, which is 5. So the order of operation is the one you would expect for real numbers. Okay, so now if you remember my previous motivating examples with a grocery store, let's define formally, and in fact, actually, let's see, yeah, probably we should do this on the second page because I want to put this together with the matrix multiplication, so stay tuned for the second page. All right, so let's talk about now about the scalar product, also known as the dot product because of the typical notation of the operation. It's denoted by like a thicker multiplication sign, hence the name dot product. This is so that it is not confused with the regular multiplication of real numbers. So this product is defined for two row or column matrices. So this is defined for row or column matrices. Pay attention here, with the same number of entries in that row or column. So how do we define it? So let's say you have a row matrix A1, A2, AN. By definition, the dot or the scalar product with B1, B2, Bn, again another row matrix with the same number of elements or entries. By definition, this is the sum of the products of each entries, A1, B1 plus A2, B2 plus so on, AN, BN. Okay, so remember the motivation as an example. When you have to find, for example, the revenue between the for the quantity sold of a various, quantity sold for products and their unit prices given in these two vectors. By the way, that's not the only, that's not like, I don't want to think that that's the most important application for it, because that's far from it. There's far more applications, far more interesting than that, that make use of this dot product. My goal with that was just to show you that this is just to serve a specific purpose, not for the fun of it. Now, keep in mind, it is always important to understand the nature of the object you're dealing with here, right? So this is a matrix. When you operate this is a matrix. The answer is a real number, right? So, when you sum up these products, you end up with a real number. So let's take a quick example. Let's say, do the dot product between 132 and 611. Again, let's write it explicitly first. Multiply each entry with the corresponding one on the other vector, and we end up with 6 plus 3 plus 2, which is 11. So that's the answer for this example. Keep in mind, unless we need to make a distinction, it doesn't matter if you write the vector, these matrices by row or by column. So if I have, for example, a row matrix and a column matrix with the same number of entries, we're going to still call this a dot product. As long as the number of entries is the same, then the way we compute it is the same. It has to do, whether you write it by row or column, again, it's not arbitrary. Which way is which depends on the context of the applications. You will see in a moment when we define the matrix multiplication, it's necessary to think of this dot product as between a row and a column, again with the same number of components. So in general, if you work with vectors, let's say you have an application just with vectors, not matrices, then it's just a matter of choice sometimes, whether you write it by row or by column, right? So for example, if I have a choice between the two, I like to write it by column, but that's just one particular taste of it. In some other cases, it's not at all arbitrary. Okay, so it has to be precisely either a row or a column. But again, when it comes to the dot product, the way you compute it is the same. What's important, of course, is to have the same number of components. So notice that, as a remark, you cannot multiply, you cannot scalar multiply, let's say the vector -1, 2 with, let's say, the vector 1, 3, 2, right? Because for obvious, I'm not going to even do it, right? So you're not going to have obviously enough matchings, right? So the last component here is not going to be paired with an entry in the first one. So you need to have the same number of components to compute the dot product the way it is defined. So The reason I actually went over this concept of a dot product first is because you will see it makes it much easier on me, and I suppose on students as well, to define how matrix multiplication is done, so that we can get to the examples quickly enough. Now, before I do that, let me just mention one extra definition, which is plays a role in geometry and some vector applications, especially in calculus 3. We say that two vectors, remember vectors are row or column matrices, so two vectors are orthogonal or perpendicular, I'll explain that in a moment, if their scalar product, their scalar or dot product is equal to 0. So for example, if I take the vector -1 represented by a row matrix, let's say -1, 3, 1, with the vector 5, 2, -1, the dot product is -5 plus 6 -1, which is 0, so they are obviously orthogonal. The reason they're called this way is because if they represent geometric vectors, the dot product being 0, it's related to the angle between them being 90 degrees. It's related to the cosine of the angle between them. And if that angle is 90 degrees, the cosine of 90 degrees is 0, so that's a consequence of that aspect. This is usually covered in calculus 3 in the beginning of the course. All right, so finally, let's define now the matrix multiplication or the product of two matrices. And I want you to pay attention, close attention here, especially if you didn't do this before, on the assumptions, on the conditions imposed on the matrices so that we can actually compute this matrix multiplication. So suppose A, given by, as usual, by the generic element Aij. So suppose A is an M by N matrix, right? So that means M rows, N columns, and B, given by the element Bij, is an N by P matrix, that is to say N rows and P columns. So notice that the restriction is that the number of columns of A must be equal to the number of rows of B. And once you see how the product is defined, it's pretty obvious why that's the case. It's because of the way those dot products are supposed to work, right? Because it's basically just a collection of dot products, this A times B. Again, go back to the examples with the produce in the grocery store. Number of rows of A, number of columns of B doesn't matter as long as the columns of A and rows of B coincide. So if these conditions are met, then the product between A and B is going to be C, an M by P matrix, right? So that means it will have number of rows of A and number of columns of B. So it's going to be an M by P matrix, and it's going to be defined in the following way. So whose element little Cij is the dot product of row I of big A and column J of B. As always, examples or an illustrated picture, a rough sketch if you want, is much better to understand how this works. So if you look at the typical in the matrix A, right? So this is the M by N matrix. So therefore a typical row of it is going to have the entries AI1, AI2 up to AIN. And in the matrix B, a typical J column, a typical column is going to have the entries B1J, B2J, right? The second index is going to be the same, BNJ, right? So notice the number of elements in that column is the same as the number of elements in the row of matrix A. This is where the condition of rows of A must be equal to, columns of A must be equal to rows of B plays a role. Because when you multiply the matrices, then these two, this row and this column, will produce the, somewhere in the middle here, the element Cij, right, corresponding to row I and column J. And as I said already in the definition, that's obtained by the dot product of that row and that column. So it's going to be AI1 times B1J plus AI2 times B2J all the way up to AIN times BNJ, right? So this is how each element is obtained. Sometimes I like to write it like this: row I dot column J, right? Because, and that's the reason why I actually like to go over the dot product. So I prefer the students just basically understand well how the dot product is computed. And then basically the matrix multiplication is just a bunch of dot products made of pairing rows of A's with columns of B. Okay, so with that out of the way, let's finish up this lecture with examples of matrix multiplication. So stay tuned for the last page. All right, so here is an example of a 2 by 3 matrix and a 3 by 2 matrix. And notice that we could compute A times B and B times A. So these are possible because the number of rows and columns, because the number of columns of the first coincide with the number of rows on the second. We're going to show you an example in a moment when the product cannot be computed, right? But for now, let's do the multiplication in this order, right? So let's do A times B first. Let me copy them one more time. All right, so 2 by 3 multiplied by 3 by 2. Check to see that these two coincide. All good. And just like before, at least for once, let's do the multiplication detail before you actually simplify it. So row 1, column 1, that comes from -1, -3, plus 0 and 2, and then 2 and 1. You may slow down here. Usually once you get used to this, you just follow the row and the column. You focus on the row and the column that you pair. And sometimes you use the two fingers to just point to the two that come in the multiplication or in the dot product. So -1 with -3, put the fingers between 0 and 2. So as you advance in the row and as you advance in the column, move your fingers so that you make sure you pair the entries correctly. One of the common mistakes if you're rushing in the beginning is to just multiply incorrectly the entries, like you pair the entries incorrectly. That's one typical mistake. Now, the other element on the same row of the product comes from row 1, column 2. So that's -1 with 1, 0 minus 5, and then plus 2 times 2. So this, obviously the answer is going to be 2 by 2, right? And then finally row 2, column 1, 2 with -3, 1 with 2, 3 with 1. and then 2 with 1, 1 minus 5, and then 3 and 2. And so let's simplify this stuff. We get 3 plus 0 plus 2, that's 5. And then we have minus 1 plus 4, 3. Next one is minus 6 plus 2 minus 4 plus 3, negative 1. And then 2 minus 5 minus 3 plus 6, that's 3. All right, let's do b times a little bit faster. Let's arrange them now first. Minus 3, 1, 2 minus 5, 1 and 2. You may want to pause this and try to do it on your own and see if you get the right answer. And then times minus 1, 0, 2 with 2, 1, 3. So now this is going to be 3 by 2 multiplied by 2 by 3. My answer is going to be 3 by 3. So we have only two products in each dot product. Minus 1 with minus 3, that's 3 plus 1 times 2. That's 5. 0 plus 1, minus 6 plus 3. That's the first row. Now row 2 with the other columns. Minus 2 minus 10, that's negative 12. 0 minus 5. And then 4 minus 15, negative 11. Row 3 with the other columns, minus 1 plus 4, and that's 3. 0 plus 2. And then 2 plus 6, which is 8. Alright, so that's going to be the b times a. So, one important remark, which is obvious from these examples, in general, you would not expect a times b to be equal to b times a, even if it's possible to compute. So it's not commutative. If a times b is possible, does not mean b times a is possible. So here's an example. We could have, let's say, again, a 2 by 3 matrix, minus 1, 0, 2, 2, 1, 3. I can combine this with any matrix that has 3 rows, right? Let me see, 3 rows, yeah. So let's say I have 3 rows and 3 columns. 6, 1, 2, minus 1, 3, 5, 0, 1, 2. So this is 2 by 3. By 3, and the answer is going to be a matrix 2 by 3, right? I'm not going to compute it. Try to do it on your own as an example. On the other hand, if I try to do it in the opposite order, 6, 1, 2, minus 1, 3, 5, 6, 1, 2, to be multiplied by minus 1, 0, 2, 2, 1, 3. That's not going to be possible because the number of columns of the first matrix is not the same as the number of rows in the second matrix. So this is not going to be possible, right? And you'll notice that if you take a row and a column, obviously you cannot do the dot product, right? Because one entry is not matched. 6, 1, 2, you cannot do the dot product with minus 1 and 2. You're missing one extra entry in the second matrix. So finally, the last remark, there is one special matrix that plays the role of 1 for multiplication. This is called the identity matrix. It is denoted by IN, so it's an n by n matrix, same number of rows and columns. By the way, these are also called square matrices. I forgot to mention this notion here. So if the number of rows and columns are the same, these are called square matrices for obvious reasons, right? Because it looks like a square with the same number of rows and columns. So the identity matrix with n rows and n columns is going to be the matrix denoted by Aij with the values, so with Aij 1 if I is equal to j, and 0 if I is not equal to j. So in other words, it's the matrix with 1 on the main diagonal. As an example, I3 is going to be the matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so all zeros except the elements on the same row and column. A1, 1, A2, 2, A3, 3. So when I is equal to j. The diagonal that starts from the left upper corner to the right down, that's called the main diagonal. So if you have ones on that diagonal and 0 elsewhere, this plays the role of 1 in the sense that any n by n matrix, if you multiply it with the identity matrix, you get the same thing. So that's the main property, and that's an important property. It plays an important role, this matrix, for obvious reasons, because it plays the role of 1, so it can work as such in matrix multiplications, matrix operations in general. We'll encounter this quite often. So let's finish with an example to just convince ourselves that it does play the role of 1. Let's do an example with a 2 by 2 case. So let's say you have 2, 1, 6, 5, a 2 by 2 matrix multiplied by the corresponding identity matrix with 2 rows and 2 columns, so 1, 0, and 0, 1. So obviously you have 2 times 1 plus 1 times 0, 2, 0 plus 1 times 1, 6 times 1 plus 5, 0, and then finally 6, 0 plus 5 times 1. So it should be pretty obvious that you end up with the same matrix, 2, 1, 6, 5. So that's it for the introductory lecture, and I'll see you next time.